Advanced Algebra 2 Semester Exam Review, Unit 9, Exponential and Logarithmic Functions. So number 1, it says solve for x. We have an exponential function here because there is a base with an exponent. So the way that you solve these first is you try to get the bases to be the same value. So right now we have two bases. We've got a base of 25 and a base of 125. We know that those are both related with 5 as its base, so we can rewrite 25 as 5 squared. We can rewrite 125 as 5 to the third. We're not changing the values, we're simply just rewriting numbers with different bases, so it's just using a different representation. So we're going to replace 25 with 5 squared, but then that still has an exponent of 3x minus 1. That will be equal to, then we replace 125 with 5 to the third. So now we've rewritten these numbers so that their bases are the same. But this still looks kind of complicated on this side. So we're going to use our exponent properties of power to a power and multiply those exponents on the left. So this 2 will be distributed to both 3x and negative 1. So we have a base of 5 to the 6x minus 2 power, and then simply 5 to the third on the right. Now we have a property of equality where we can say that if this value is supposed to be equal to this one, when their bases are the same, that means that this exponent must also be equal to this exponent. So what that lets us do is simply ignore the bases, and we're not canceling them, we're just ignoring them, and we're focusing on their exponents. 6x minus 2 must be equal to 3. And then we simply solve the algebraic equation linear that we have in front of us. With exponential functions, we have a domain of all real numbers. It has a horizontal asymptote at 0, and there would be the graph. And so the domain goes from negative infinity to infinity without excluding any values. So this means that every input is possible, which means there is no possibility for extraneous, so we do not have to check our solutions here. Number 2, solve for x, still an exponential equation, but this time I have something else that is not attached to the exponent on the same side. So we need to isolate whatever's being affected by the exponent before you can start messing with bases. So in this case, we're going to simply divide out the 2. We end up with 3 to the x is equal to 9. Now in this case, you can change the bases like we did before, or we can just ask ourselves 3 to what power makes 9, and we all know that that's going to be a 2. So let's just do it like we did a minute ago and just check that it's a 2. So we're going to change 9, and we'll rewrite 9 as 3 squared. So 3 to the x will be equal to 3 squared. And again, property of equality, we can ignore the bases, and we can say that x is equal to 2, just as predicted before. Then we're going to solve logarithmic equations. Solving logarithms involves either changing them into their exponent form or using a property of equality. In this case, because there is a single number over here, there's not a logarithm, we're going to be using the inverse of a log, which is an exponent. So we're going to take this equation and we're going to change it into its exponent form. That involves us locating the base, so the base would be 3. And the answer to a log is always an exponent. So we're going to take 3 and raise it to the 4th power, and that will equal what's on the inside, or the argument. And again, we have a simple linear equation. 3 to the 4th is 81, equals x minus 5. Add x to cancel out, or add 5 to cancel out the negative 5, and we end up with 86 is equal to x. Now, unlike exponentials, logarithms have a vertical asymptote, which means that they have a restricted domain. Their domain is everything greater than 0. So we have to check. We need to make sure that whatever we got for x, when we substitute it in for the argument, that is a result bigger than 0. So to check, we're going to take 86 and plug it in. 86 minus 5, and we're going to check that that is larger than 0. We get 81, and that is in fact bigger than 0, so 86 is a real and good solution. Number 4, we have another logarithmic equation. In this case, there are no what I call free numbers. All of these values are inside of logarithms, this x and this 16 included. And so this is going to involve a similar property of equality as we did with exponents. But first, there's too many logarithms on the left. We need to condense this side down into a single logarithm. So because there's a plus in the middle, that lets us know that we're going to be using our product property. The product property states that if two individual logs are added, you can condense them into a single by multiplying their insides. So this is going to condense into log base 2 of x minus 6 times x. Because the right-hand side is simply a single logarithm, that does not need condensing. Before we move on, let's simplify the left. So we got x times x, so we end up with log base 2 of x squared minus 6x, and that will equal log base 2 of 16. So similar to the property of equality for exponents, we have a log base 2 that is supposed to be equal to another log base 2. So if those two numbers are equal, what that means is that these insides, the arguments of the logs, must also be the same. So simply, just like before, we can ignore the logarithms and focus on the arguments. X squared minus 6x equals 16, and solve the equation that is resulting. This is a quadratic, so we're going to try to solve by factoring. We end up with an a value for x squared, b negative 6x minus 16 equals 0, and we're going to attempt to solve by factoring. A times c will be negative 16, b is negative 6. So we need two numbers that multiply to negative 16, but also add to negative 6. We end up with negative 8 times 2. And that will produce our factors. X minus 8 times x plus 2 is equal to 0. So in order to solve these, we take each factor and we set it equal to 0. X minus 8 equals 0, x plus 2 equals 0, and solve the individual equations, resulting with a solution of x equals 8 and x equals negative 2. But again, because we have a logarithmic equation, we must check our solutions. So in order to check, we must plug in each of these answers into the logarithm's arguments and make sure that they are all greater than 0. Anything that results in at least one argument less than 0 or equal to 0 must be rejected. Let's start with 8. So we have 8 minus 6. We're hoping that's bigger than 0. That's going to be 2, and 2 is in fact bigger than 0. So far, so good. Then we must plug it into this one. 8 greater than 0, which is true. So 8 is a good solution. We don't need to worry about 16 because 16 does not involve an x. Then start with negative 2. I'll do it in orange. So negative 2 minus 6 greater than 0. Negative 8 greater than 0. That is not true, which means that negative 2 is an extraneous solution. So the only solution we have for equation number 4 is x equals 8. Number 5, fully condense the logarithmic expression. So condensing involves taking lots and lots of logarithms and smushing them down into preferably one. In order to do this, we have to make sure that our bases are the same. So look at all the logarithms in the expression and make sure they're all the same base. We have log with no base, which means that it's the common log, so it is assumed to be a base of 10, which they all are, so we're good in that case. When you are condensing, the first thing you're going to try to do is get the exponents back. So exponents look like numbers multiplied to the front of logarithms. That means that if there's a number multiplied in front, that was actually an exponent. So 2 was the exponent on x, and 4 was the exponent on y. So we have log of 4 plus log of what really was x squared before it got expanded, and this is really y to the 4th. Then we look across all the logarithms and see what is in between them. So all 3 of these have plus signs in between. That means we're able to use that product property that we talked about earlier. If you have 2 logs, log of A plus log of B, you are able to condense those by multiplying their arguments. And that goes for 3, 4, 5, 12 logs. As long as there's pluses in between them, they all get multiplied on the inside. So we will have log of 4 times x squared times y to the 4th. And because there are no more logs outside of this 1, there's nothing left to condense, so this would be your final condensed expression. You also don't need the dots. You could simply just put 4x squared y to the 4th. That is also acceptable. Lastly, we're going to expand and simplify as far as we can. So this one has a fraction on the inside. Fractions are considered one solid piece. In order to be able to simplify the numerator and denominator separately, we have to separate the fraction. And there is a quotient property that lets us do that. So the quotient property says if you have the log of a divided by b, we can expand that by taking the logarithm of the numerator and subtracting the logarithm of the denominator. And that lets you look at the numerator and denominator individually. So when you expand, you keep all the bases the same. That way you can condense it back together. So because this is starting out as log base 2, every logarithm we expand into will also have a base of 2. So we have log base 2 of the numerator, 3x to the 5th, minus log base 2 of the denominator, z squared. Then we look and see if we're going to do the product rule or if we're going to do the exponent rule, the power rule. It depends on where the exponent sits. So because the 5 is here on the inside, it is just affecting x, not the 3. If the 5 was outside, then it would affect both, and that would change the order that we apply. But because the 5 is just affecting x, we actually have to break these apart first with the product rule and then worry about the power rule. So the product rule says that if you've got if you have two things multiplied on the inside, you can break that apart by adding two separate logs with one argument each. The order does not matter here. So because 3 is multiplied to x to the 5th, I can expand that as log base 2 of 3 plus log base 2 of x to the 5th. And then for now, we're just going to bring down log base 2 of z squared since I haven't done anything with that one just yet. Now we can perform the power rule on any exponents that might be on the logs. So the power rule says, again, if you have a to the n on the inside of a log, that the exponent can come down in front and multiply to the logarithm in the front. So this 5 will come down to the front and multiply. This 2 will also come down to the front and multiply. So we have log base 2 of 3 plus 5 times log base 2 of x, so that used to be the exponent, minus 2 from the exponent, log base 2 of z. And because each logarithm has a single number on the inside, that will be the fully expanded expression.